Have you ever stopped to think about sound? Really think about it. When you speak or sing or clap your hands, what's really happening? You're making vibrations. Tiny, invisible wiggles in the air, molecules all around you. These vibrations travel through the air like ripples in a pond, and when they reach someone's ears, their brain translates those wiggles back into sound. It's pretty amazing, right? But here's the thing. Those vibrations don't travel very far. If you shout, someone across a field might hear you, but someone across town, not a chance. The energy just fizzles out. It's a fundamental challenge of communication. So how do we solve this problem? How can we send our voices, our music, our ideas over vast distances, even across oceans and continents? We can't just shout louder. We need a better way. We need a way to hitch our sound vibrations onto something much more powerful, something that can travel really, really far without losing its energy. Think of it like trying to send a paper boat across a huge lake. Tossing it from the shore won't work, but what if you could put that little paper boat on top of a big, powerful speedboat? That speedboat could carry your tiny boat all the way to the other side. That's the basic idea behind radio. This is where science gets really cool. We figured out that we could use electricity and magnetism to create invisible waves, radio waves. These are a type of electromagnetic radiation, just like light, but with a much longer wavelength that our eyes can't see. These waves are our speedboat. They can travel at the speed of light and go for hundreds, even thousands of kilometers. But a plain, empty radio wave isn't very useful. It's just a silent, constant hum of energy. To send information, we need to put our message, our sound vibrations, onto that wave. We need to modulate it. The process of adding our information onto a powerful carrier wave is called modulation. It's the key to all radio communication, from the music you hear in the car to the signals that let your phone connect to Wi-Fi. It's how we take a local vibration, like a singer's voice, and encode it onto a wave that can circle the globe. There are a few different ways to do this, but one of the first and most clever methods ever invented is called amplitude modulation, or AM for short. It's a simple, elegant solution that changed the world and helped build the foundation for our modern connected society. Consider this. So, let's break down this big idea. Amplitude modulation. It sounds complicated, but we can understand it by looking at the words. First up is amplitude. Imagine a wave in the ocean. The amplitude is how tall that wave is, from its calm middle point to its highest peak. A big, powerful wave has a high amplitude, and a small, gentle ripple has a low amplitude. In a radio wave, amplitude represents its strength or intensity. A high-amplitude radio wave is a strong signal, and a low-amplitude one is a weak signal. It's the power of the wave. Simple enough, right? Next, we have the word modulation. To modulate something just means to change it or vary it in a specific, controlled way. When you're talking, you modulate your voice. You make it louder or softer to add emphasis. You change its pitch to ask a question or make a statement. You are constantly modulating the sound waves coming from your mouth to carry meaning. So when we put these two words together, amplitude modulation literally means we are going to change the amplitude, the strength of our radio wave in a very specific pattern to carry our information. We're making the powerful wave stronger and weaker to match the pattern of our original sound. To make this happen, we need one more key ingredient, the carrier wave. The carrier wave is our powerful, high-frequency radio wave. Think of it as a blank canvas. On its own, it's just a steady, unchanging wave with a constant frequency and a constant amplitude. It's our speedboat, running at a steady speed. It carries the energy, but not the message. The information we want to send, like a voice or a song, is a much lower frequency sound wave. This is our message signal, our little paper boat. The magic of AM is in using the message signal to control the amplitude of the carrier wave. Here's how it all comes together. An AM transmitter takes the powerful carrier wave and the weaker sound wave and combines them. Wherever the sound wave is loud, has a high amplitude, the transmitter makes the carrier wave stronger, gives it a high amplitude. Wherever the sound wave is quiet, has a low amplitude, it makes the carrier wave weaker, gives it a low amplitude. The resulting AM wave is a high-frequency wave whose overall shape, its envelope, perfectly matches the original sound wave. It's our speedboat, now speeding up and slowing down in a pattern that perfectly mimics the journey of our paper boat. Let's imagine your favorite song is playing on an AM radio station. The singer's voice, the guitar chords, the drum beats, all of these are just complex sound waves. At the radio station, a microphone converts these sounds into an electrical signal, a perfect electronic copy of the music. This electrical signal is our message. Meanwhile, the station's powerful transmitter is generating a carrier wave at its specific frequency, say 770 kHz. This carrier wave is just a pure, constant electronic hum waiting for instructions. It's ready to do the heavy lifting and travel through the air. Now, the modulation happens. The transmitter looks at the music signal. When the singer hits a loud high note, the transmitter boosts the amplitude of its carrier wave, making it super strong. When there's a moment of silence or a soft, quiet part of the song, the transmitter reduces the amplitude, making the carrier wave weaker. This process happens thousands of times per second, perfectly tracing the intricate shape of the music onto the strength of the radio wave. The radio station is now broadcasting a high-frequency wave that is throbbing in sync with the music. The music is literally riding on top of the carrier wave. This modulated wave then travels out from the station's antenna at the speed of light. It can travel over hills and around buildings, spreading far and wide. Your car radio, or the old radio in your grandparents' garage, has an antenna to catch this wave. The first thing the radio's receiver does is tune into the specific frequency of the carrier wave, that 770 kHz we mentioned. This is what you're doing when you turn the dial. You're telling your radio to ignore all the other stations and listen only for that specific carrier frequency. It's like picking one specific speedboat out of a whole harbor full of them. Once your radio has locked onto the carrier wave, it performs the opposite process, which is called demodulation. It has a special circuit, called a detector, that looks at the incoming wave and ignores the fast, high-frequency carrier part. Instead, it just pays attention to the changes in the wave's amplitude, its overall shape or envelope. It traces that shape and converts it back into an electrical signal. This new electrical signal is a nearly perfect replica of the original music signal from the studio. This signal is then amplified and sent to the speakers, which vibrate and turn it back into sound waves that you can hear. And just like that, the music that was in the studio is now in your car. Science! Amplitude modulation was a brilliant start, but it's not the only way to modulate a wave. It's part of a whole family of modulation techniques. Perhaps its most famous sibling is frequency modulation, or FM. As you might guess from the name, FM radio works differently. Instead of changing the amplitude, or strength of the carrier wave, a FM transmitter keeps the amplitude constant and changes the frequency, which is just the number of wiggles per second, of the wave instead. When the original sound signal is loud, the frequency of the carrier wave increases slightly. When the sound is quiet, the frequency decreases slightly. This difference leads to the distinct qualities of AM and FM radio that you've probably noticed. AM signals, with their changing amplitude, are more susceptible to interference from other electrical sources, like lightning or sparks from machinery. This interference also changes the amplitude of the signal, and the radio receiver can't really tell the difference between the noise and the original signal. That's why AM radio can sometimes sound crackly or full of static. FM, on the other hand, is much more resistant to this kind of noise. Since the information is stored in frequency changes, not amplitude changes, the FM receiver can just ignore most static spikes, resulting in a cleaner, higher fidelity sound. However, AM has its own advantages. AM radio waves, especially at lower frequencies, have a fantastic ability to travel very long distances. The signals can bounce off a layer of our upper atmosphere called the ionosphere, allowing them to travel over the horizon and be heard hundreds or even thousands of kilometers away at night. This is why you can sometimes pick up a distant Clear Channel AM station from another city after the sun goes down. FM waves, being much higher in frequency, travel in a straight line, like a beam of light, and are generally limited to line-of-sight distances, usually no more than about 100 to 150 kilometers. Beyond AM and FM, we now live in a world of digital modulation. Techniques like quadrature amplitude modulation, or QAM, which you'll find in your cable modem and Wi-Fi router, are even more advanced. These methods can change both the amplitude and another property of the wave, called its phase, at the same time. This allows them to pack an incredible amount of digital information, ones and zeros, onto a carrier wave. It's like not only controlling the speed of our speedboat, but also making it swerve left and right in a specific pattern, carrying far more information on a single trip. All of these modern marvels, however, stand on the shoulders of the simple, powerful idea first pioneered by AM. With the crystal clear sound of FM radio, satellite radio, and endless streaming services, it might be easy to think of AM radio as a relic of the past, a charming but outdated technology. But even today, on June 14, 2025, AM radio continues to play a vital and often unseen role in our world. Its simplicity and resilience are its greatest strengths. An AM transmitter is relatively simple and cheap to build and maintain compared to more complex systems. And as we discussed, its ability to cover enormous geographical areas with a single transmitter is an advantage that modern technologies struggle to match efficiently. This long-distance capability makes AM radio incredibly important for emergency broadcasting. When natural disasters like hurricanes, earthquakes, or widespread power outages strike, other communication systems like cell towers and internet lines can fail. But a well-placed, powerful AM station with its own generator can stay on the air, broadcasting vital information, safety instructions, and updates to the public over a huge region. Government emergency alert systems around the world still rely on the AM band as a primary, robust way to reach citizens when all else fails. Its simplicity means even a simple battery-powered or hand-cranked radio can pick up the signal. Furthermore, the AM band is the home of many niche and community-focused broadcast formats that thrive on its unique properties. Talk radio, news stations, sports broadcasts, and religious programming have long been staples of the AM dial. For these formats, the crystal-clear audio fidelity of FM is less important than the broad reach and the loyal, engaged audience that AM provides. It allows a single station to serve an entire metropolitan area or a vast rural region, creating a shared community conversation that is difficult to replicate with shorter-range broadcast methods. It remains a powerful tool for communication. So, while AM may not be the way most of us listen to our high-fidelity music anymore, its work is far from over. From its historical significance as the technology that first brought instantaneous news and entertainment into our homes, to its ongoing role as a lifeline in emergencies and a voice for communities, amplitude modulation is a testament to the power of a simple, brilliant scientific idea. It taught us how to make waves talk, and those waves are still talking today. And that is a truly remarkable piece of science. Consider it.